In the vast expanse of the cosmos, there exist objects of unimaginable power and brilliance. These celestial wonders, known as quasars and blazars, shine with the intensity of trillions of suns. Quasars and blazars are not merely distant stars. They are the radiant echoes of supermassive black holes lurking at the hearts of galaxies. Imagine a beacon so bright that it could outshine an entire galaxy. These objects are cosmic engines, fueled by the insatiable hunger of supermassive black holes. As matter falls into these gravitational abysses, it releases an extraordinary amount of energy, lighting up the surrounding regions. By studying quasars and blazars, astronomers can trace the evolution of galaxies and the growth of supermassive black holes over cosmic time. The discovery of quasars in the 1960s revolutionized our understanding of the cosmos. Astronomers were baffled by these enigmatic objects, which appeared as point-like sources of radio waves but were far too distant to be stars in our own galaxy. Initial observations revealed that quasars were receding from us at incredible speeds, implying that they were located at vast distances. The realization that quasars were extragalactic objects with astonishing luminosities sent shockwaves through the scientific community. As matter spirals inward toward a supermassive black hole, it forms an accretion disk, a swirling disk of gas and dust. While both quasars and blazars are powered by supermassive black holes, they exhibit distinct characteristics that set them apart. Quasars, short for quasi-stellar radio sources, were first identified by their strong radio emissions. Blazars, on the other hand, are a type of quasar characterized by their extreme variability and powerful jets of energy. The key difference between quasars and blazars lies in the orientation of their jets relative to our line of sight. Blazars are oriented such that one of their jets is pointed directly towards Earth. This alignment results in a phenomenon known as relativistic beaming, where the jet's emission is amplified and appears much brighter than it would otherwise. At the heart of every quasar and blazar lies a supermassive black hole, an object of immense density and gravitational pull. These cosmic behemoths are not mere holes in space, as their name might suggest, but rather regions where gravity is so strong that nothing, not even light, can escape their grasp. Supermassive black holes are thought to have formed in the early universe from the collapse of massive clouds of gas and dust. Despite their invisible nature, we can detect supermassive black holes by their gravitational influence on surrounding matter. As stars and gas clouds venture too close to a black hole, they are caught in its gravitational clutches. This process of accretion releases tremendous amounts of energy, powering the brilliant displays of quasars and blazars. Supermassive black holes are not merely passive bystanders in the cosmic drama. They are active participants, shaping the galaxies they inhabit. Their gravitational influence extends far beyond their immediate surroundings, affecting the orbits of stars and gas clouds across vast distances. In fact, astronomers believe that most, if not all, massive galaxies harbor a supermassive black hole at their center. It can trigger star formation, drive galactic winds, and even regulate the growth of the galaxy itself. The relationship between supermassive black holes and their host galaxies is a complex interplay of gravity, energy, and matter. This outward pressure can counteract the inward pull of gravity, creating a delicate balance that determines the fate of the galaxy. As matter spirals inward towards a supermassive black hole, it forms an accretion disk, a swirling vortex of gas and dust heated to millions of degrees. The material in the accretion disk is not falling directly into the black hole, but rather orbiting it at incredibly high speeds. Collisions between particles in this cosmic maelstrom generate friction, which in turn produces heat and light. Similarly, as matter spirals inward in an accretion disk, its orbital velocity increases, generating immense amounts of kinetic energy. This energy is converted into heat and light, causing the accretion disk to shine brightly. In the case of quasars and blazars, the accretion disks are so luminous that they can outshine their entire host galaxies, making them visible across billions of light-years. The energy released by accretion disks is not limited to heat and light. In some cases, powerful jets of charged particles are ejected from the poles of the accretion disk, perpendicular to its plane. These jets, traveling at nearly the speed of light, are thought to be collimated and accelerated by magnetic fields threading through the accretion disk and black hole. These jets can extend for millions of light-years, far beyond the confines of the host galaxy. As they travel through interstellar and intergalactic space, they interact with surrounding gas and dust, creating shockwaves and bubbles of hot gas. These interactions play a crucial role in the evolution of galaxies, influencing star formation and the distribution of matter in the universe. Imagine a lighthouse, its beam cutting through the darkness, guiding ships to safety. Now, imagine that lighthouse so powerful that its light could be seen from across the universe. That's the basic idea behind a quasar, a celestial object so luminous that it outshines entire galaxies. Quasars are like cosmic floodlights, their light illuminating the vast reaches of space. As matter falls into these gravitational behemoths, it swirls around, forming an accretion disk, a cosmic whirlpool of gas and dust heated to millions of degrees. By studying quasars, astronomers can peer back in time, observing the conditions that existed when galaxies were young and the universe was a much more active place. Not all quasars are created equal. Astronomers have discovered different types of quasars, each with unique characteristics that provide clues about the underlying physics at play. One important distinction is between radio-loud and radio-quiet quasars. Radio-loud quasars, as their name suggests, emit strong radio waves in addition to their visible light. These emissions are thought to originate from jets of charged particles ejected from the accretion disk at nearly the speed of light. The reasons for this difference are still not fully understood, but they likely involve the properties of the black hole, the accretion disk, and the surrounding environment. Imagine a flashlight beam pointed directly at you. Now, imagine that flashlight is a blazar, a type of quasar with its jet pointed directly towards Earth. This alignment results in a phenomenon known as relativistic beaming, where the jet's emission is amplified, making it appear much brighter than it would if viewed from a different angle. Blazars are like cosmic lighthouses with their beams aimed straight at us. The study of blazars is crucial for understanding the physics of relativistic jets and the behavior of matter in extreme environments. Quasars and blazars are more than just dazzling displays of cosmic power. They are also powerful tools for studying the universe's history. Their immense distances mean that the light we observe from them has been traveling for billions of years, offering us a glimpse into the distant past. By analyzing the spectrum of light from quasars and blazars, astronomers can probe the composition and distribution of matter in the early universe. Their study is crucial for unraveling the mysteries of our cosmic origins and understanding the grand narrative of the universe. To study objects as distant and faint as quasars and blazars, astronomers rely on some of the most powerful telescopes ever built. These instruments, located both on Earth and in space, act as our eyes on the cosmos, collecting the faint light that has been traveling for billions of years. Ground-based telescopes like the Keck Observatory in Hawaii and the Very Large Telescope in Chile use massive mirrors to gather light. However, Earth's atmosphere can distort and absorb light, hindering observations. To overcome this, astronomers also rely on space-based telescopes like the Hubble Space Telescope and the recently launched James Webb Space Telescope. Quasars and blazars don't just emit visible light, they radiate energy across the entire electromagnetic spectrum, from radio waves to gamma rays. To get a complete picture of these objects, astronomers observe them using telescopes sensitive to different wavelengths. Radio telescopes, like the Very Large Array in New Mexico, detect the radio waves emitted by quasars and blazars. At the other end of the spectrum, gamma-ray telescopes, like the Fermi Gamma Ray Space Telescope, detect the highest energy radiation from quasars and blazars. Gamma rays are thought to be produced in the most extreme environments, close to the black hole, and their detection provides clues about the processes occurring in these regions. While telescopes are our primary tools for studying quasars and blazars, astronomers also rely on other techniques, such as spectroscopy and interferometry, to extract more information from the light they collect. Spectroscopy involves splitting the light from an object into its component wavelengths, like a prism separating sunlight into a rainbow. By analyzing the spectrum of a quasar or blazar, astronomers can determine its chemical composition, temperature, and velocity. Interferometry, on the other hand, involves combining the light from multiple telescopes to create a virtual telescope with much higher resolution. While quasars and blazars are incredibly luminous, the supermassive black holes at their hearts are, by definition, invisible. However, astronomers can still study these enigmatic objects indirectly by observing their effects on the surrounding matter. One way to study black holes is by observing the orbits of stars and gas clouds around them. By carefully tracking the motion of these objects, astronomers can infer the mass of the black hole and the shape of its gravitational field. Another way is to study the radiation emitted by the accretion disk as matter falls into the black hole. This radiation can be used to probe the properties of the accretion disk, the black hole's spin, and the presence of magnetic fields. By combining these different techniques, astronomers are gradually piecing together a more complete picture of supermassive black holes and their role in the universe. In the cosmic ballet of the universe, quasars and blazars take center stage, their brilliant light revealing the intricate dance of supermassive black holes. Recent observations have provided stunning evidence for the existence of binary supermassive black holes, two gravitational behemoths locked in a gravitational embrace. Imagine two spinning tops placed close together, their axes slowly precessing around each other due to their mutual gravitational attraction. Similarly, binary supermassive black holes orbit each other, their gravitational pull creating ripples in the fabric of spacetime, gravitational waves. These waves carry away energy, causing the black holes to spiral closer together over time. Astronomers have discovered binary supermassive black holes by observing periodic variations in the brightness of quasars. These variations are thought to be caused by the orbital motion of the black holes, which periodically alters the amount of light emitted from their accretion disks. As our telescopes become more powerful, we can expect to discover more of these binary systems, providing crucial insights into the formation and evolution of galaxies. Quasars, distant beacons from the early universe, reveal conditions when galaxies were young. Observations show quasars from when the universe was less than 1 billion years old. Imagine the first stars and galaxies just beginning to form. The universe was chaotic, with quasars as signposts of early galaxy formation. Studying these quasars helps astronomers understand early universe properties. The universe, as we understand it, is composed of matter and energy. The vast majority of this matter is in the form of dark matter, a mysterious substance that doesn't interact with light. The rest is baryonic matter, the stuff that makes up stars, planets, and even ourselves. However, there's a problem. Astronomers have found that the amount of baryonic matter we observe in the universe is significantly less than what our current cosmological models predict. This discrepancy is known as the missing baryon problem. Recent observations suggest that quasars and blazars might hold the key to solving this cosmic mystery. The powerful jets emanating from these objects heat up the surrounding gas, preventing it from cooling and forming stars. This heated gas, known as the warm-hot intergalactic medium, WIM, is difficult to detect directly but could account for a significant portion of the missing baryons. The study of quasars and blazars is a dynamic and rapidly evolving field, with new discoveries constantly reshaping our understanding of these enigmatic objects. Future telescopes and observational techniques promise to revolutionize our view of these cosmic beacons, unlocking even more secrets of the universe. The upcoming Square Kilometre Array, SKA, a massive radio telescope being built in Australia and South Africa, will have unprecedented sensitivity and resolution, allowing astronomers to study quasars and blazars in unprecedented detail. The SKA will be able to detect fainter and more distant quasars, probing even further back in time to the early universe. Meanwhile, the development of new technologies, such as adaptive optics and machine learning, is enhancing the capabilities of existing telescopes, enabling astronomers to make more precise measurements and extract more information from the data they collect. With these advancements, we can look forward to a future where our understanding of quasars and blazars and the universe they inhabit continues to expand at an accelerating pace. As we gaze up at the night sky, we are not just seeing stars scattered across a velvet canvas. We are peering through a cosmic time machine, witnessing light that has journeyed for billions of years. Quasars and blazars, luminous beacons from the early universe, whisper tales of a chaotic cosmos. Powered by supermassive black holes, they offer glimpses into intense cosmic activity and growth. Astronomers use them as cosmic probes, revealing secrets of the early universe. The study of quasars and blazars is a quest to answer fundamental questions about our universe. How did the first galaxies form? What is the nature of dark matter and dark energy? How do supermassive black holes grow, and what role do they play in galaxy evolution? These questions drive astronomers to study these enigmatic objects. By unraveling their mysteries, we gain a deeper understanding of the universe. Quasars and blazars are not isolated phenomena. They are integral threads in the vast cosmic tapestry that connects everything in the universe. Their powerful jets, emanating from the depths of supermassive black holes, inject vast amounts of energy into the surrounding intergalactic medium, influencing the formation of stars, the growth of galaxies, and the overall evolution of the cosmos. Imagine a spider web, its delicate threads intricately woven together, each strand connected to the others. Similarly, quasars and blazars are part of a complex web of cosmic connections, their influence extending far beyond their immediate surroundings. By studying these connections, we gain a deeper appreciation for the interconnectedness of the universe, recognizing that even the most distant and seemingly insignificant objects can have a profound impact on the cosmic web. Our exploration of quasars and blazars is far from over. It is an ongoing journey of discovery, driven by our insatiable curiosity and our desire to understand the universe we inhabit. With each new observation, each new discovery, our picture of these enigmatic objects becomes clearer, but the universe always has more surprises in store for us. As we continue to build bigger and better telescopes, develop more sophisticated observational techniques, and refine our theoretical models, we can look forward to a future filled with exciting new discoveries about quasars, blazars, and the universe they illuminate. These discoveries will not only deepen our understanding of the cosmos, but also inspire future generations of scientists and explorers to continue pushing the boundaries of human knowledge. The study of quasars and blazars is a testament to the power of human curiosity and ingenuity. It is a reminder that we are part of something much larger than ourselves, a universe filled with wonder, mystery, and endless possibilities for exploration and discovery.